Now we get to the feature speaker of our evening, Dr. Scott Denning, and he is one of the most down-to-earth atmospheric scientists I know of. He is a Monfort Professor of Atmospheric Science at Colorado State University. He is author of more than 100 papers in the professional climate literature, and he served on advisory panels for the U.S. Department of Energy, NASA, NOAA, and the National Science Foundation. As a young man, he was a geologist working in the oil industry in Montana and North Dakota. And he spends weekends at a mountain cabin where he photographs distant galaxies. I would love to do that. Scott, are you ready?
Yep.
To go?
Ready when you are.
Okay.
So would you confirm you can see my screen?
I can.
So I got 3 things to talk about this evening about climate change, and they all start with the letter S, so it's kind of easy to remember. The 3 S's of climate change are simple, serious, and solvable. Simple is how does it work? Serious is why is it bad? And solvable is what are you going to do about it? Now, it's a little strange that somebody like me who's been working on this for like 35 years would say it was simple. Because if it's so simple, how come I still have a job? But really, the basic story of how climate works is stuff you learned in grade school. It's not stuff that you have to go to grad school for. And I know that all of you are plenty smart to understand this. You don't need a lot of fancy words and computers and graphs and stuff. So we're going to talk about simple. We do have to talk about serious in the middle because it is a serious problem. But then I promise we will get to solutions by the end because we don't want to just dwell on the doom and gloomy stuff. So let me just start by asking, did you ever wonder why day is warmer than night? Or why summer is warmer than winter? Or why Phoenix is warmer than Fargo? No, you probably didn't wonder about this because you already know the answers to these questions. But if you just think about it for a minute, bear with me. The answer to all 3 questions is the same. Day is warmer than night, summer is warmer than winter, Phoenix is warmer than Fargo because when more heat goes into something than comes out, it warms up. And when more heat goes out than comes in, it cools off. This is sort of the basic story of how weather and climate work. It's a heat budget, right? So I understand that it's springtime. I mean, in Montana, just like it is here in Colorado. And sometimes we have beautiful, sunny 80-degree weather, and sometimes we have snow. We had snow here a couple of weeks ago in Fort Collins, where I live as well. I understand you have some snow in northern Montana today. But those big changes that we have day to day, that's all about heat coming in and going out the sides, right? The air that was here yesterday that was nice and warm blows away, goes somewhere else, and it's replaced by colder air from upwind. And that's what weather is, really. Weather is all about these fronts and air masses moving around. But when you look at the Earth as a whole, look at the planet and consider the climate of the entire world, there are no sides, right? The Earth is round. It doesn't matter how much sideways heat motion you get on a round ball, it's still the same amount of heat. You're just redistributing it. The only way that the Earth can get heat in is through the top. And of course, that's from the sun. And we all know about that. You know, I feel it on my bald head shining down and gives me sunburn and I feel warm. But if that was the whole story, right? Heat in minus heat out equals change of heat. If that was the whole story, the Earth would just get hotter and hotter and hotter because that's only heat in. There has to be heat going out. And the only way the heat can get out, again, is out to outer space. Now, the difference is you can't see that outgoing heat like you can see the incoming sunshine because the outgoing heat is in a part of the electromagnetic spectrum we can't see. It's called the infrared. It's heat rays beaming out to space and carrying the heat out. And if there's an imbalance in those 2 big arrows, the heat coming in, if that's greater than the heat going out, the Earth warms up. If the heat going out is greater than the heat coming in, the Earth cools off. And that's the story of climate change. Heat in minus heat out equals change of heat. So you can sort of imagine here's just a cartoon of this. You got some gigantic wood stove in your living room, but in your attic, you got no insulation, right? So the heat in minus the heat out equals the change of heat. You can imagine that the house in this particular picture might be kind of chilly because there's a lot of heat going out the top. On the other hand, if you put a whole bunch of insulation in the attic up there so that you stop the heat going out, it's still the same fire down in the living room. It's still the same amount of heat in, but because you've slowed down the heat going out, you have a change in heat and the house will warm up. And that's precisely what we're talking about with climate change. Now, I got one little thing that you probably didn't learn about in grade school, and I got to explain it to you. And I'm sorry about getting kind of sciencey on you here for a couple of slides, but I promise that that this part's over with quick. The sun can get through the air, and we know that because we can see where we're going, right? Visible light, we call it visible because we can see it, and it's transmitted through the air. The air is transparent and visible because almost the whole air is made of these two gases. The top one's called oxygen and the bottom one's called nitrogen. And 99% of the molecules in the air are these diatomic molecules, two atoms of the same element. They're glommed together. These little lines here supposed to be shared electrons going back and forth, and that's a chemical bond holding that together. And the infrared energy coming up from the surface going out to space can interact with these shared electrons. Electromagnetic fields get the electrons going back and forth. You can sort of think of it like balls on a spring, kind of goes woo, woo. Doesn't really make that sound. I just make that part up. But the woo woo thing is now a transformed piece of energy that was going out to space, and now it's the vibrational energy of that molecular bond. But because 99% of our air is just these two diatomic molecules, that's the only way they can wiggle. The only dance they know is to get longer and shorter along that molecular bond. On the other hand, there's just a teeny tiny amount of these two other gases in our air. But the thing about these two gases, this top one's called carbon dioxide and this bottom one's called water, right? H2O. And the thing about these gases is that they've got 3 atoms instead of 2 atoms. And a 3-atom molecule has more ways to wiggle than a 2-atom molecule. So I only have the 2 hands. Kristen, can you see me? Can you guys seeing me?
Yes, yes.
Okay, so let's let my head be carbon, and here's oxygen, and here's oxygen, okay? Along comes some infrared radiation going out to space, and it grabs a hold of those shared electrons and goes woo, 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 woo. So that has transformed the outgoing radiation into the wiggly, vibrational energy of the molecule. And then it can be re-emitted either up or down and either cool the earth if it goes up or warm the earth if it comes down. But unlike O2 and N2, the 3-atom molecules got more tricks, more dances on its dance card. It can go wee, boom, wee, boom, wee, boom, wee, boom, wee, boom, wee. Each one of these different ways of wiggling this molecule absorbs a different wavelength of infrared radiation, a different energy level of outgoing photon that's going out to space. And that's what makes CO2 a greenhouse gas. It's not greed or capitalism or Al Gore. It's just bad luck that the stuff that comes out when you set carbon on fire has 3 atoms instead of 2 atoms. And so there's more ways you can wiggle it. Water vapor is even better. It's got this thing going and this thing and this thing, all these different ways of wiggling that water molecule. But of course, the thing that happens if you put extra water vapor in the atmosphere, it rains. And there's no such thing as CO2 rain. So the water vapor only lasts a few days in the atmosphere, but the CO2 is forever. It just stays up there. It accumulates more and more and more and more. The more carbon we burn, the more CO2 there is in the air. And because it absorbs that outgoing radiation, it's like insulation for the earth. It actually holds the heat of the earth. So you've probably seen this cartoon before. The sun beats down. That's what warms the earth. Part of it reflects off, but the part that doesn't reflect off gets absorbed. And that's heat in, right? That's the part that warms us up. And if that was the whole story, the earth would just get hotter and hotter and hotter until it would like melt and boil and vaporize and be the end of the world. So luckily that's not the whole story. You got these red arrows and those are the infrared heat that's going out. And some of it does, in fact, just pass through the atmosphere, but the atmosphere is pretty much opaque in those red arrow infrared rays. It's transparent to the yellow rays, but it's opaque in the red rays. The red rays, most of them, about 94% of them get stuck by either water vapor or CO2 molecules in the atmosphere. And eventually it radiates out the top, but a whole bunch of it gets radiated downward. And I have in my office a radiation measurer. And if I went outside at night and stuck that, I've done this with my students, measure the radiation coming down from the sky. At night, there's no sun, but the warm sky is constantly radiating down on us like a heat lamp up in the sky. It's just like the little heat lamp outside your shower that keeps you warm. And our warm sky keeps us warm 24/7. That's the greenhouse effect. If it weren't for the greenhouse effect, the world would not be a habitable planet. The whole oceans would have frozen over long ago, and we wouldn't be here talking about it. So brings me to what I call the common sense explanation of climate change. Many of you probably old enough to remember these things. This is an incandescent light bulb. This one in particular is the kind we used to use for night lights for my kids to help them find the bathroom at night. These were 4-watt incandescent light bulbs. Nowadays, of course, it's all LEDs, but back in the day, we had 4-watt light bulbs. And if you double the amount of these beep boo molecules up in the sky, that would add this much extra heat, 4 watts to every square meter of the earth. Now, what's a square meter? You know, it's about 3 feet on a side. Look down around you, find something that's about 3 feet on a side. For me, it's my desk. I can imagine a little night light bulb in the middle of my desk, but it wouldn't just be my desk. It would be there and there and there and there and there, and not just my office and not just Colorado and not just Montana, but the entire planet covered with little 4-watt light bulbs every 3 feet. And you're going to leave those light bulbs on 24 hours a day, 365 days a year for the rest of your life. And if you did that, that would make the world a little bit warmer. Now, maybe not a lot warmer because they're just night light bulbs, but it sure as heck wouldn't be zero. And that's exactly why we know that adding CO2 will warm the climate. Believe it or not, all of that was known before light bulbs were even invented. The first laboratory measurements of this effect were made during the US Civil War in 1863 by a guy named John Tyndall in New York City. And he put CO2 in a glass bottle, and he shined infrared light, and he measured how much infrared light was absorbed by the CO2, and he added more CO2 and measured how much more it absorbed and so forth. And he did this for all kinds of different gases. And he wrote a famous paper 165 years ago explaining that if we burned a whole bunch of coal, it would add CO2 to the atmosphere and warm up the climate. So this isn't something we discovered like 20 or 30 years ago and got all concerned about. This is something that was predicted when Abraham Lincoln was president. So it brings me to what I call common myth number 1 about climate change. It's dangerous to tell you guys a myth because you're going to remember the myth and you're going to forget that it was a myth, right? So watch out, I'm going to say something that's not true. The not true thing is that scientists are so sure that the future is warmer because it's been warming up recently. And of course, it has been warming up recently, and most climate change talks will start with a graph like this, right? Long time ago, it was colder, and then it got warmer, and then recently it's been getting warm really fast. Well, that's all true, but remember, we knew this was going to happen when Abraham Lincoln was president. No, we're not just shooting this line out into the future. We know that adding CO2 will warm the climate because we know that when you add heat to things, they change their temperature, right? This is like the formal name for this principle is the first law of thermodynamics. The add heat to something and it changes its temperature. But honestly, that's a pretty egotistical thing to say. First law of thermodynamics. And for God's sakes, cavemen knew this, right? They put the mammoth on the fire and it got hot. But they didn't say first law of thermodynamics. They said ugh, hot. So we know that adding CO2 to the climate will warm the world because we understand the law of ugh, hot. Okay, so much for simple. Now I have to tell you the serious part, and nobody likes talking about this, right? It's no fun. We wish it weren't true, but it is a serious problem, and it actually becomes a more and more and more serious problem until we stop making it worse, and then it doesn't get better. So it may not be the worst problem in the world now, but if you just keep doing it, it will eventually grow to be the most serious problem in the world. How much warmer are we talking about? Well, it depends, right? If we don't burn very much, it doesn't get much warmer. If we burn more, if we burn even more, these maps show how many degrees Celsius of warming in this century in different emission scenarios. But look at the maps. The first thing you might notice is that it gets a lot more warming on the land than it does in the oceans. And that's because the oceans are deep. The oceans on the average are 13,000 feet deep. And you put a 4 4-watt light bulb on top of 13,000 feet of water doesn't do very much, because there's this tremendous mass in that ocean that's soaking up all that heat. And it's hard to warm up 13,000 feet of water. So the land warms up more. Notice that the northern hemisphere warms up a lot more than the southern hemisphere. That's because the northern hemisphere is mostly land and the southern hemisphere is mostly ocean. And then the third thing, if you look really carefully, you see that the snowy, icy places get way more warming than any place else. And that's because snow and ice are bright and white and they reflect sun to space. And if you warm up enough to melt the snow and ice, well, then you can soak up some extra sunshine too. And it's not just the 4-watt light bulb from the extra CO2, it's also all that extra sun that you can absorb because you're not reflecting it back from the snowpack. So here in the low emissions world, in the middle of North America, maybe 3 degrees Celsius of warming. Here in the high emissions world, maybe 6 degrees Celsius of warming. And that doesn't sound too terribly bad, but we certainly warm up more than other places because we live on land in the north where it snows, right? We get extra. We get quite a bit more than the global warming. So say 3 to 6 degrees Celsius here in North America. But wait, you guys don't do Celsius at home, right? I'm a scientist. I don't even do Celsius at home. I listen to the radio in Fahrenheit. So if you convert 3 degrees to Fahrenheit, that's 5 degrees Fahrenheit, or 6 degrees Celsius, about 10 degrees Fahrenheit. So we're talking 5 or 10 degrees. And even that doesn't sound too terribly bad. You know, if I don't know what it was like in Montana today. Here in Fort Collins, it was about 75. It was 85. You know, I probably would have had to mow the lawn earlier in the morning, but I could probably live with 10 degrees warmer today. We're not just talking about today. We're talking about on the average 10 degrees. The only way you can get your head around that is to look at a map. Okay, here's a map of average temperatures in the United States in Fahrenheit, and each color on the map is 5 degrees Fahrenheit warmer than the color next to it. So I've got Great Falls, Montana on here. I've got Champaign, Illinois. I got Washington, D.C. And what I'm going to do is I'm going to move each of those dots 2 colors on the map to simulate 10 degrees Fahrenheit of warming. And geez, Louise, that's actually quite a lot. That's like you guys moving to Winslow, Arizona. It's like me moving to Albuquerque. It's like moving to Illinois farms down to Mississippi, or Washington, D.C. down to Florida. It's like moving 1,000 miles south. And you don't think, farmers in Eastern Montana or ranchers in Eastern Montana are going to notice if somebody swaps in the climate of Winslow, Arizona for the climate of Great Falls. I got another thing to tell you. I mean, that's a lot of change. So it's not just like a particular day being 10 degrees warmer. It's like moving 1,000 miles south. Around here, of course, we don't have to go south or north to get different temperatures. We can go uphill and downhill, right? We live in the Mountain West, where we've got, shrublands up to foothills and montane forests and alpine and so forth. Each 3,000 feet of elevation here in the Mountain West is about 10 degrees Fahrenheit. So if I'm telling you you're gonna change the climate or warm the climate by about 10 degrees Fahrenheit, that means like you're gonna move downhill by 3,000 vertical feet. So think of the climate of Sydney out on the Eastern Plains, out by the North Dakota border, moving to Bozeman, right? That's about 10 degrees Fahrenheit, about 3,000 feet. Or Great Falls, moving all the way up to the top of Going to Sun Road in Glacier National Park. Or Cook City up in the mountains, moving to the top of the Beartooth Highway. And imagine that happening in 2 generations of people, not 100 centuries like it took at the end of the last ice age, but like in 1 century. That's a ginormous amount of change. And there's not enough time for the plants and the animals and the landscapes to adapt to change of 3,000 vertical feet here in our mountains. We happen to live in a part of the world that's very vulnerable to this because we have just enough water. There's 75 million people who live in the area covered by this map. This is a map of annual precipitation in the Western United States. And, most of it's pretty darn dry, right? We're down here in the 12, 15 inches of rain a year, rain and snow. But the reason that 75 million people can live on that map is because of these blue places on the map. And you know what those blue places are? They're mountains. And the mountains stick way the heck up in the sky, and they gather the water vapor as it goes by, and they turn it into snow, and that snow melts this time of year, and it comes down and fills our reservoirs. And that's how we support our crops, and that's how we support our cities. That's how we support a civilization here in the semi-arid West. because we have this tremendous amount of water that accumulates in our mountains every winter. It takes like 8 months to fill up that gigantic reservoir, much bigger than we could build a reservoir. We have a natural reservoir sitting up there waiting to run down and fill our reservoirs down on the plains and provide tap water and irrigation water for our civilization. Our snowpack has been declining already. We've only had about 2 degrees Fahrenheit of warming up to now. You can imagine what 10 degrees more would look like. These different colors are all different snow stations up in the mountains, and the red ones have declines of more than 50% in peak snowpack over the last 40 years. So there's a fair number of those. The yellow ones aren't, the orange ones aren't as bad, only a 20% decline. There are some green ones and blue ones that are actually increasing with time, but the predominant pattern here in the West is that we are losing our mountain snowpack already, even though we've only had a little bit of climate change yet. But there's much more to come. The real killer is evaporation. Okay, so we think about drought being a lack of rain, but really drought is more than just a measurement of rainfall. Drought is the difference between water in and water out. Just like heat in minus heat out equals change of heat, water in minus water out equals change of water. And if you've got 10 degrees warmer air, like you move to Winslow, Arizona, you're gonna lose a lot more water. You're gonna need more water. Your water demand goes up. It's a matter of supply and demand. And unless your water supply increases dramatically, you can't keep up with warming like moving 1,000 miles south or moving 3,000 feet downhill. It's very, very difficult to supply the water that we need here in the West if we didn't have the climate that we have. If you warm things up equal to moving 3,000 feet downhill, you are really going to notice that water. The other thing, of course, that we've seen in recent years is that the warming promotes wildfire. And there's really kind of 3 things. First of all, as I've already described, the warmer air increases the evaporative demand. You're pulling more water out of those forests every day, all summer long. And you know, they get this huge flush of water this time of year during the melt, and that fills up the soil pores, and those trees have to get through the whole darn summer on the water that they store in the spring when the snow melts. But every day during a warmer summer, you're sucking more water out of that soil. The other thing is that the warm season, the evaporation season, is much longer, right? Instead of just having supporting the trees from, let's say, June, July, and August, maybe now you got May and September as well, or even April and October. So this longer warm season with more evaporation every day depletes that soil moisture. You get to the end of the season, it's all crunchy under your feet and it's ready to burn. The third thing is that, you know, those really bad fire days where it's like 99 degrees in the shade and 4% relative humidity and blowing 50 miles an hour, those days happen way more often in a hot summer than they do in a cool summer. And those are the days where the fire comes sweeping down the mountain and into a subdivision, and they have to evacuate everybody, and the firefighters have to run away. Those kind of 3, like triple whammy here, puts a tremendous amount of fire stress on Western forests. And this is a study from the National Research Council that shows for every 1 degree Celsius of warming, what percentage of increase in burned area every summer. And you can see, so I talked about like up to 5 degrees Celsius of warming. So that's 5 times this much, 2,500%. Imagine 25 times as much acreage burning every summer. What happens, of course, is you run out of stuff to burn, right? Eventually you're burning a forest more often in a shorter period of time in between fires than it takes to grow the trees. And at that point, you've basically lost the forest. You've replaced them with something else. And it's not necessarily something good. It's like switchgrass, or it's yucca or something like that. So actually a tremendous increase in fire area over time as things warm up. I got one more kind of bummer thing to tell you about, and that is essentially that the warming is a one-way trip. So I told you I wasn't going to use too many graphs. This is a graph, sorry about that. But these are actually crazy scenarios that go all the way out to the year 3000 AD. So you can see here we are in 2020, and we could have emissions, CO2 emissions go down to 0 here in the next 30, 40 years. Or on the other hand, we can just burn it like there's no tomorrow, and then wait until whatever, 22nd century to turn it down. But in all cases here, the CO2 emissions are going to 0 by the end of by about the year 2300. But look what happens to CO2, almost nothing. CO2 stays in the atmosphere for literally for thousands of years after we're done burning. It's like you got your hand on a thermostat, but there's a ratchet in there. You can turn it up, but you can't turn it back down. Once it goes up, it's going to be up there for a really long time. So we have to stop burning before we get to these super high levels of CO2 that will make it very, very hard for us to continue having a prosperous economy. Okay, so let's talk about Solvable. What are we going to do about this? How are we going to get out of this mess that we're in? If every bit of carbon that we burn turns into CO2 and that CO2 doesn't go away, but it traps heat forever, what are we going to do? We're going to stop setting stuff on fire, right? This is really kind of the main thing to do, is that, and it's not just you and not just me, it's everybody everywhere forever making money and living good lives without subsidizing our lifestyles with fossil fuels. And in order to do that, there's sort of two techniques. One is to use energy wisely, and the other is to make energy that doesn't involve combustion. And luckily, we got some ways to do that. But I got to tell you, when I say everybody everywhere, I mean everywhere. These are two photographs of Shanghai in China. Shanghai is the most populous city on earth. There's 22 million people in Shanghai proper, and there's surrounded by suburbs. Each suburb has more than 10 million people, and you've never heard of one of those suburbs. 75 million people in the Shanghai metro area. These are two pictures taken 20 years apart in Shanghai. And what you're seeing there is not population growth. What you're seeing there is economic growth. And that's good, because we've got billions and billions of people who've been desperately poor for a long, long time. They're energy poor, and they are now coming to join the party and be part of our modern energy use. There's about 7.5 billion people on Earth, but there's only 1 billion people like us that use a lot of energy. And the trouble is there's going to be 4 billion people like us by the end of this century. So the population's actually growing pretty slow. We expect maybe 30% population growth by 2100, but 300% increase in the amount of energy people use, because people are climbing out of desperate poverty. This is a good thing. This is spreading capitalism and freedom and liberty, and people are living better lives. But if they do that by burning coal, oil, and gas, we're going to be in a world of hurt. Energy use is growing 10 times faster than population around the world. Turns out in the developed world, we use most of our energy either building buildings or operating buildings. It's sort of an amazing thing. We think of our cars, but actually our buildings use almost twice as much energy as all of transportation in the developed world. And that's, of course, mining the ore and smelting the steel and making the I-beams and transporting around, hanging the drywall, everything. Plus your heating and lighting and air conditioning and all that stuff. So there's a lot of room for improvement in buildings. And luckily, there's a tremendous amount of low-hanging fruit there. These are some projections of the US Department of Energy. They thought we would be using more and more energy in our buildings out here till 2030. That was their projection in 2005. In 2007, they thought we'd use a little less. In 2009, 11, and 12. You see what's happened here is that our expectations of energy use in buildings have gone way down. And it's not because we're shivering in the dark. It's because we got better lights and better windows and better air conditioners and better roofs and all that stuff. And just this one change alone, in the US alone, is going to save us $4.5 trillion over the next 20 years in energy we were planning to waste, and we don't need to waste it anymore. The other thing, of course, that's happening is that the way we make energy is changing dramatically. Just in the last 10 years, since I started doing these presentations, the price of solar and wind power have fallen by like 90%. Amazing, tenfold. Imagine if other stuff was 10 times cheaper than it was in 2010. Imagine if your car cost 1/10 today what it cost in 2010. That's what has happened in the energy markets, and it's changing the world. Without subsidies, you cannot afford to burn coal or even natural gas, because wind and solar without subsidies are much, much cheaper than coal or gas. Here in Colorado, we had a couple of big power plants in Pueblo that are going offline because they've reached end of life. Big coal-fired power plants, about 600 megawatts of juice. And Xcel Energy went out for bids to replace that 600 megawatts of power. They expected to put in gas turbines and combined cycle gas there, but it turned out that the wind with battery storage absolutely beat the pants out of the gas for new power here in Colorado in 2018. 2 cents a kilowatt hour for wind power with storage over the lifetime of those plants, less than half of the cost Xcel was paying to operate their existing coal-fired power plants that they had bought and paid for. So you can build new wind and operate it for 30 years for less than half the price that you can keep the old coal plants running. Now, this is going to cost some money, okay? Conversion to 100% non-carbon energy is likely to cost about 1% of the economy. And when I say the economy, I mean the world economy. So you probably don't even know how much the world economy is worth, but you could guess what's the total value of all the goods and services sold in the world in a year? It's a lot. It's about $85 trillion a year. And 1% of that is a boatload of money. But, you know, there's a picture of a toilet on here. It's not a suggestion. I'm just going to compare the 1% of GDP we're going to spend on reinventing energy with what it costs to retrofit all the world's cities with indoor plumbing a century ago. Imagine the cost if you had to do that today, right? Dig up every street in New York and London and Paris and lay sewer pipes and knock out tenement walls 20 stories high and put in, you know, hot and cold running water, knock out all the internal partitions in those flats and put in toilets and sinks and showers. And boy, are we glad they did that, because now we got toilets and sinks and showers. And they spent a boatload of money. But where did that money go? It went to plumbers. It went to plumbing suppliers. It went to the grocery store down the street from the plumber, or the children of that plumber who could use it to go to college. I mean, money is never gone in a capitalist system. It goes round and round. And one person's spending is always another person's earnings. And this is how infrastructure works. Here's 1% of global GDP, $850 billion a year. That's a lot of money, right? Guess what? We spend almost that much on mobile phones. I don't mean just like your Verizon bill. I'm talking the phones themselves. We spend almost $800 billion just buying brand new phones. Cars and trucks, my God, $2 trillion a year. Coal, oil, and gas, we spend $4,000 billion a year on coal, oil, and gas. So yeah, it costs a lot of money to save our economy, but it's not more than we're already spending on other stuff. This is kind of right in the ballpark of what we're already spending on stuff. These are my grandparents. That's Max and that's Francis. And it was their generation that did the indoor plumbing. And when they were done with indoor plumbing, they did rural electrification, right? What do you think it would cost if you had to pay union wages today to string separate little copper wires to every farm in eastern Montana or Nebraska? What do you think it cost to do this back in the 1930s? It was really expensive. When they were done with the subways and the sewers, they fought the Nazis. You know, this is the greatest generation. This is my parents. That's Margie and that's Bob. And their generation did big things too. They did the interstate highway system. They fought the Cold War. They sent people to the moon. And these things didn't bankrupt my parents' generation. These things were the source of prosperity in my parents' generation. They were most of the job growth in my parents' generation. This is me and my wife, Jennifer, back when I had hair. And our generation did it too, right? We spent boatloads of money, trillions and trillions of dollars, putting computers on every desk in every office on earth, billions and billions of computers every 3 years. Geez, when we were done with that, we replaced every landline on earth with cell phones, and we invented the internet. And none of these things ruined the world economy. In fact, these things were the world economy during my entire adult life. This is where all the job growth came from. This is why my retirement plan is worth more than it was when I was 30. So these are my kids. That's Matt and that's Nate, and they get to do it again. They get to reinvent the world's energy system and replace a system that's decrepit and falling apart and built in the 19th century with a new smart grid that can deliver clean power to everyone that needs it and raise the standard of living of people around the world and produce all the jobs and prosperity of their generation, just like my generation, just like my parents and my grandparents' generation did. You can choose how you think about history, right? A lot of people think our well-being is propped up subsidized by stuff we dig out of the ground. That a lump of coal is worth money, and you sell it to somebody and they set it on fire, and the energy is worth money, and they sell the energy to somebody that makes products and services that are worth money, and you wheel and you deal, and pretty soon you got yourself an $85 trillion a year global economy. And maybe that is the way history works, but God, I hope not, because that story has a terrible, tragic ending. If we live by burning coal, what happens when it runs out? Do our descendants just shiver in the dark? Do they go back to the Middle Ages, only now there's 10 billion of them? I hope not. That's a tragic story, a sad way to think about human history. I prefer this one. We create our well-being. We don't do it out of stuff we dig out of the ground. We do it through creativity and ingenuity and hard work. It's not through subsidies of stuff we dig. It's from the smarts in our brain, the sparks in our soul, and the sweat of our brows. And our kids can do that just as well as we did, and just as well as our parents did, and their future is going to be bright. Thank you for your time.
Wow. You take a break there, Scott, or you get some water. And I wish we could have everybody unmuted, because I bet they'd be like yelling and screaming and saying, oh my God, I'm so glad I came to this webinar. So I can't thank you enough for empowering us, for informing us, and just mind-boggling. It's going to probably take a while to get everybody figuring that out. But anyway,